All right, for the first question, we're asked to pick the compound which is the strongest acid. In this case, we have carboxylic acid functional groups on all of the compounds. So thinking about our REO, for our atom, we have two oxygen atoms which would have the negative charge when thinking about our conjugate base. So our atom is pretty much the same for all of these. For resonance, we also have two contributors for all of these. So if we deprotonate one of these hydrogens, we're going to end up with our carboxylate anion. And for resonance contributors, this is one of the contributors. The other is where we bring our electrons down, push these electrons up, and that would give us our resulting resonance contributor. So that's pretty much the same for all of them. For induction, that's really what determines which one of these is the most acidic. So in terms of inductive effect, it's going to be the most electronegative atom which has the most inductive effect. So in this case, fluorine is our most electronegative atom. This is going to be the strongest acid because, again, for atom and resonance, we were tied with all of these compounds, but our most inductive electronegative atom directly attached to something close to where our electrons, our negative charge from our conjugate base would be, is the fluorine atom. So this is the strongest acid for those reasons. For the next compound, we're asked to select the compound with the highest boiling point. In this case, so boiling point is based on molecular weight as well as interaction potential. So we have things like dipole interactions as well as hydrogen bonding interactions, where hydrogen bonding is the most prominent of the two. So it looks like for compounds 1 through 4, we have dipole-dipole interactions as well as hydrogen bonding interactions for all of them. For compound 5, we have pretty much nothing, which is van der Waals interactions. So looking at compounds 1 through 4, the molecular weight is pretty similar for all of them. Actually, 4 has a slightly higher molecular weight. The most important thing is, though, that hydrogen bonding potential for compound number 4 is basically doubled. So this can essentially hydrogen bond with a proton that's around it. Like if, let's say, we had a carboxylic acid functional group, it could bond with the OH of the carboxylic acid functional group. And then again, this hydrogen could also hydrogen bond. So if we have a carboxylic acid functional group, as I've drawn right here, that hydrogen can hydrogen bond with the oxygen of the carboxylic acid functional group. So based on number 4 having a higher molecular weight as well as the most hydrogen bonding potential, that is the compound with the highest boiling point. Now you can always check that on Wikipedia if you want to look up these compounds. So this one is 1, 2, 3, 4, 5 carbons. So pentanal, which we'll look at that more once we get into chapter 12. This is 1, 2, 3, 4, 5 carbons with a ketone at carbon number 2. So this is 2-pentanone. Again, we'll look at that more. Hopefully you remember the name for that. And this is what we just looked at naming. So this is 1, 2, 3, 4, 5 carbons. So pentane, but we take off the E and make it oic acid. So this is pentanoic acid. And that carbon right there is carbon number 1. All right, for question number 3, list the general name as well as the specific example of 4 types of carboxylic acid derivatives. So for this, we have our acyl chloride, and then next we have our acid anhydride, and next we have our ester, which has an R group attached to the oxygen, very similar to the carboxylic acid, which instead of an R group has an OH group. And then finally we have our amide, which is an amine attached to a carbonyl carbon. Now that amide can have substituents on it, so we could have like an N-methyl substituent, or the most simple amide is just an NH2, where essentially we ignore that for naming and assume hydrogen is going to fill in the gaps. All right, list the general name. So I said these, but let's go ahead and write them out. So this is an acyl chloride. And keep in mind, we have a halogen attached, but we're only going to talk about acyl chlorides in this chapter. For this one, this is an acid anhydride. And this compound here is an ester. In our notes today, we talked about how And ester is different than an ether. Remember, an ether is an oxygen with two R groups attached. An ester is a carbonyl carbon with an OR group attached to it. So this is an ester. In this case, this is a carboxylic acid. And this is an amide. So talking about how they are named, so let's look at the ester, carboxylic acid, and amide. So for this compound, we have our carbon chain is an ethyl group. So if this was a carboxylic acid, well, first of all, if it's just a two-carbon chain, it's ethane. If it's a carboxylic acid, we take off the E, and so this compound right here is So normally we would say ethane, but we take off the E and specify the carboxylic acid functional group. So again, take off the E and add oic acid. So this compound is ethanoic acid. For this compound right here, for our amide, again, we have ethane. We take off the E and replace that with amide. So this compound is ethanamide. And for our ester, in this case, we specify what that R group is. So I'm actually going to replace this with a methyl. So that's my methyl group right there. And in this case, we specify what is attached to the oxygen, and then we name the parent chain, the parent compound, which is our ester. So for these, we end it in O8. So this is going to be methyl ethan, and then we take off the E and end that in O8. So methyl ethanoate. For the order of reactivity, I've already listed these in order of reactivity. So the acyl chloride is first, the acid anhydride is second, the ester is third. Now in the book it says it's tied with the carboxylic acid, but I'm going to say the carboxylic acid is fourth anyway. That oxygen with a negative charge on it is slightly less stable than the ester. And the amine is fifth. And then also for the carboxylic acid, we've got that acidic proton. So if we have strong base, strong nucleophile coming into attack, most likely it's going to be a proton transfer rather than reacting with this carbonyl carbon. The acyl chloride is ranked first. When we kick off our conjugate base, that chlorine with a negative charge is by far the most stable. Now the acid anhydride is remarkably stable as well. So once we attack this carbonyl carbon and we kick off our leaving group, in this case, our leaving group, so in this case, our leaving group was, I don't know why I drew that. So in this case, our leaving group is Cl minus, very stable. In this case, our leaving group is essentially a deprotonated carboxylic acid. So our leaving group is a carboxylate anion. When we have the negative charge in the oxygen, like we talked about above, we can show resonance between these two. Unlike our ester, where in this case our leaving group would be our O-methyl group. So now we also have a negative charge on an oxygen, but no resonance potential. For the carboxylic acid, remarkably similar. We have an OH. That hydrogen is going to pull slightly less electron density than a carbon chain can. And then for 5, our amine leaving group. And again, I said amine leaving group. So rather than an amide, we'll call this an amine. Whether we have this be an NH2 with a negative charge, or even if we have methyl groups on there, that nitrogen is less electronegative than oxygen, so that's going to be less stable. All right, for the next, predict the major products for each reaction. If this was bleach, if this was HOCl, we would form an aldehyde. This is a stronger oxidizing agent. It's chromic acid. This is going to form a carboxylic acid. So we're going to fully oxidize that carbon that had the alcohol functional group. So that's the product for that. For this reaction here, if we've got that hydrogen, like we talked about above, for the carboxylic acid, that's a little bit tricky. If we have a strong nucleophile, strong base, for all the other derivatives, we'd attack the carbonyl carbon. In this case, we're going to do a proton transfer. deprotonate that to form our carboxylate anion. And then also the byproduct of this includes our ethanol, so our protonated ethoxide. So we've got our carboxylate anion plus then our ethanol. For the next one, here we actually have a negative charge on the oxygen. This is a fairly stable conjugate base, but this is actually a strong nucleophile. We do not have a nucleophile here, so there really is no nucleophile that can attack that carbonyl carbon. Also, this is a somewhat bulky nucleophile, so it's somewhat limited. It probably wouldn't attack a carbonyl carbon even if we had something that was less sterically hindered than this. So for this, we're going to use our electrons to do a nucleophilic attack on that primary carbon and kick off our leaving group, which will get us to our product, which we've converted our carboxylate anion into an ester, specifically a propyl ester. All right, for the next question, oftentimes the book represents this as being two equivalents of this. The reason why is so it can show that proton transfer. We covered a reaction very similar to this in our notes today. So let's go ahead and just draw the first step of the mechanism, and then I'll talk about the second step. After we do that nucleophilic attack, we need to deprotonate this nitrogen. So once that nitrogen is bonded to that carbon, it's going to have a positive charge, and that proton needs to be deprotonated by another equivalent of this, or you can just write in B and use that to deprotonate your nitrogen. Eventually, though, this is the worst leaving group once we deprotonate that, so our O propyl group is going to get kicked off. So that means for this, our final product is going to be our amide product rather than our ester. So now our nitrogen is attached. That has a methyl group and an ethyl group attached to it. For this, NaCl, we have our chloride anion. Chlorine, looking at the strength of the nucleophile, is not a very strong nucleophile. Most importantly, it's a very stable base. So when we're kicking off one of these compounds, so if chlorine attacks there, chlorine is more likely to get kicked back off rather than nitrogen. Nitrogen would be a very strong base, so that's why that would not get kicked off. So this one is no reaction. And for the next step, so for this one, we're going to transform this into a carboxylic acid, but I'm going to go ahead and show the full mechanism for this and basically run it down here and then get us back to our carboxylic acid. So for this, the mechanism is a little bit longer than what we've seen. So in this case, since we have a strong acid, we're going to protonate our carboxylic acid derivative, in this case our amide, before we get started. So we're going to take the hydrogen of the hydrochloric acid, and then those electrons are going to go to the chlorine to get us to our intermediate, which is this compound here. So now our oxygen, we still have that double bond there. Now our oxygen has a positive charge on it because we protonated it with that hydrogen, and we still have our nitrogen with our ethyl group and our methyl group. Now, we've seen before that the amide carboxylic acid derivative is the most stable. So there really isn't a great nucleophile that can come in and attack this to kick it off, because essentially once we kick this off, we form a very strong base. So when we think about this, the reason why we have to protonate that is so that now a weaker nucleophile can come in. So if we hadn't protonated this, the nucleophile can't come in. Now that we've protonated this, the nucleophile can come in and do the attack. We have a weak nucleophile, water, so water is going to come in the next step and attack our carbonyl carbon and push those electrons up, which gets us to our next intermediate, and now we have our tetrahedral intermediate where we have an OH group, we have an OH group which is protonated, and we have our nitrogen with a methyl and an ethyl group attached. Now we need to do a couple proton transfer reactions. So after water attacks, we need to use a weak base to deprotonate our most acidic proton, which is that one right there, and push those electrons up to get us to our next intermediate, which we still have our 6-membered ring, we still have our OH group, and our nitrogen with our methyl and ethyl, and now we have another OH group attached. Once we've deprotonated that and formed HB, and now in this case my base was neutral, now my base has a plus charge, and we have a proton on it. Now this, I only meant to draw one lone pair there. Now the lone pair on the nitrogen can come in and deprotonate that to get us to our next intermediate, which is my cyclohexane ring. I still have my OH there. Now my nitrogen is protonated, so we've got NH with a methyl and an ethyl, and now a positive charge on it, and we still have an OH group there. In the next step, still not the last step, now my electrons can come back down. I can reform my carbonyl carbon and kick off my good leaving group. This isn't a great reaction, but heat is going to help us reach the energy level necessary to get to this point, to get us to our almost product. So we've got our cyclohexane ring, and now we have our double bonded oxygen, and that's protonated, and that is attached now only to our OH group. So we have deprotonated our HB again, so we've got our base, which can deprotonate that hydrogen and deprotonate that, which can get us to the final product now, which is our carboxylic acid. All right, now for the last reaction, there are a lot of steps here, but if we go back up and look at all the steps, we actually just did all these steps. So in this case, for the first one, we had a primary alcohol. We used chromic acid to make a carboxylic acid. Once we had that carboxylic acid, we used our ethoxide to deprotonate it. It didn't do a lot for us, but we did transform our carboxylic acid into a good nucleophile. That nucleophile then reacted with our alkyl halide, kicking off the leaving group, putting a methyl group, transforming our carboxylate anion into an ester. Once we had that ester, this ester is still reactive, specifically with an amine. So if we have two equivalents of our amine, we can transform our ester into an amide, which we did here. This didn't really help our stepwise process. I just wanted to emphasize that our amide is a very stable carboxylic acid derivative. So if you have a weak nucleophile, if you have a stable conjugate base, it is not going to react. So this was no reaction. That was basically left out of this stepwise process. And in the next step, then we transformed our amide functional group back into a carboxylic acid. So thinking about this last reaction, after step one, we would transform this into a carboxylic acid. Once we have our carboxylic acid, we would deprotonate that and transform it into a carboxylate anion. Once we have that carboxylate anion can be a strong nucleophile and attack the carbon of our propyl chloride and kick off our chlorine leaving group. So again, just as we've shown up here, oxidize our primary alcohol into a carboxylic acid, deprotonate our carboxylic acid to make that a nucleophile, react that nucleophile with a substrate with a good leaving group to form an ester functional group. So after step three, we have our ester functional group. We can add an amine and convert that into an amide functional group. No need to add salt because it doesn't do anything anyway. And then the final step, if we want to get back to our carboxylic acid functional group, we need to add our water, HCl, and heat. So again, after step one, we formed a carboxylic acid functional group. If we go through all 5 steps, we also form a carboxylic acid functional group. So the product of this reaction, going through all 5 steps, is our carboxylic acid. So that's the answer. If you were asked to do a stepwise synthesis of this to make the carboxylic acid, it'd be a lot easier if you just basically started out with this, and you have to do that anyway through the process to get there. But anyway, the product of this reaction, thinking about all 5 steps, is the final carboxylic acid.